hypergraphs. Yes, looks very interesting. So whenever you're ready, you can start.
Okay. Hi everyone. Today I'm talking about our recent archive paper, Magic of Quantum Hypergraph States. Here is the context. We start with the introduction of quantum magic and quantum hypergraph states. Then we come to the main results, including the magic of arbitrary hypergraph states, or random hypergraph states, and the special hypergraph states. Now let's go to the first part, the introduction of magic. Magic has a strong connection with the so-called stabilizer formalism. A stabilizer of a pure state is a Pauli operator which such that psi is its +1 eigenstate. Conversely, a stabilizer state should have n independent stabilizer generators, and they generate abelian groups. It is not hard to find that the stabilizer states, the stabilizer generators, and the stabilizer group should be connected with a simple formula. From this, we could find that once the stabilizer generators are fixed, the corresponding stabilizer state is also fixed. That is, we can record the stabilizer state by recording its generators. In this way, stabilizer states are classically similar. In this sense, magic, or called non-stabilizedness, should be a kind of quantum resource. In simple terms, it characterizes the deviation of quantum states from stabilizer states. There are various metrics to evaluate magic, and in this work, we use the recently proposed stabilizer range entropy with a straightforward reason. It is convenient to do theoretical analysis, especially for random states. As its name shows, stabilizer range entropy is a kind of range entropy, not on the dense matrix representation, but on Pauli-Hilbert representation. For pure states, the terms trace p rho over 2 to the n sums over to 1, so we can regard them as a probability distribution and define the corresponding range entropy. And from the stabilizer formalism, it is not hard to find that stabilizer states are the extreme point of the probability distribution. Then with the offset of stabilizer states, we can use it to explore. For pure states, the terms trace rho over 2 to the n sum to 1. So we can regard them as a probability distribution. With the probability distribution, we can define the corresponding range entropy. And from the stabilizer formalism, it is not hard to find that the stabilizer states are the extreme point of the probability distribution. Now, adding of offset minus n, we can use it to evaluate magic. Then we come to introduce hypergraph states. Before it, we shortly revise the stabilizer states. The stabilizers of stabilizer states should be an element of Pauli group, and the condition that they form a abelian group is naturally satisfied since Pauli operators are either commute or anti-commute. Now we want to generalize the definition. Generalized stabilizers only need to be involutory rather than polymetrics. Yet, now the abelian group constraint of generalized stabilizers is crucial and cannot be implied. Then the relation between stabilizers and the stabilizer states still hold for generalized ones. Graph states are typical stabilizer states, and hypergraph states, their generalization are generalized stabilizer states. Their definition needs non-Clifford gates, generalized CZ gates. Similar as graph states, each vertex corresponding to a plus qubit, and each hyper edge implies a generalized CZ gate on the corresponding qubit. As the figure shows, One edge is just Z gates, and two edges are CZ gates, and three edges CCZ gates, and so on. With the generalized stabilizer formalism, we can also find its generalized stabilizer generators as it in graph states. The ith stabilizer is that X on the ith qubit and all the connective generalized CZ acting on the adjacent qubits itself. As the right figure shows, the stabilizer S1 is just X1, CZ, 2, 3, and Z4. After introducing magic and hypergraph states, we need to provide some reason why we study them. First, for FQC, for Torrent quantum computing, Eastern-New's theorem tells us that we cannot realize universal transversal gates with a simple quantum error correction code. The most common solution is to realize Clifford transversal gate with some CSS code and a non-Clifford gate with magic state distillation and injection. Hypergraph states can be used to implement generalized CZ gates and play an important role in FQC realization. For poly-MBQC, a kind of memory-based quantum computing scheme, to realize universal quantum computing, we need to measure poly operators on at least 2D magic states. For instance, hypergraph states are typical resource states of it. It was shown that poly-MBQC need magic resource states, but they shouldn't have too much magic. So the study of magic of hypergraph states is crucial to MBQC. In addition, magic is related to quantum phase, topological order, non-equilibrium dynamic, quantum chords, and black holes in quantum many-body physics. And since hypergraph states have clear graph representation and mathematical structure, they are suitable toy model to study magic in these areas. Then we come to our main result. First, for an arbitrary given hypergraph states, we provide a method to calculate its stabilizer range entropy. We call the definition of it by defining the parts inside the log as a lowercase m. We can find that the central task to calculate those trace PGG as the final line shows. For convenience, we also label P with two binary vectors X and Z. Then we define our induced hypergraph with vector X and Z, G star X, Z, to calculate the trace PGG. The formal definition is a little bit complicated and not intuitive enough. Here we only give an example of a fixed X and Z. First, for those one edges are only determined by the vector Z. Just like the Z has one on its first and fourth bit, then the Z gate applies on the first and fourth qubit. Then the other edges are only determined by vector X. They are generated by the original hyper edges, deleting a subset of vertices that corresponding to 1 in X. For example, vertices 1, 3, 5 corresponding to 1 in X. Then by deleting 1 in hyper edge 1, 2, 3, we can get the edge 2, 3 in the induced hypergraph. And also by deleting the third nodes, we get the hyper edge of 1, 2. Also notice that two same hyper edges will cancel out here. We connect those trace PGGs with the trace of hyper edges of the induced hypergraphs. Here, UGXZ is the generalized CZ unitary acting on the plus states in the definition of hypergraph states. Then by summing them up, we can get the formula of SRE. You may doubt that the computational complexity is still exponential. First, notice that M alpha G itself for any alpha or all the trace PGG could give a complete characterization of G. This part of exponential complexity is inevitable if we want a general formula. But in the calculation of trace PGG, we reduce the complexity a lot, since U is a z-diagonal phase state described by a hypergraph whose trace can also be calculated efficiently. In addition, although those using the algorithm to calculate the magic of any given hypergraph state is inefficient, we can get some useful bound from it by its generality. This theorem is an example. It tells us that the hypergraph with a bounded average degree, its SRE should also be bounded. That's to say, hypergraph states with a constant bounded average degree can never reach the maximum possible magic, or the high random states magic, n minus small o n. It is consistent with the results in polyambiguity. In polyambiguity, the resource hypergraph state should be like class state, which has only local connections, and of course constant bounded average degree. Then the magic is not too large, such that cannot exceed the PVP complexity. The proof intuition is that for hypergraph with bounded average degree, the induced hypergraph should have less multi-qubit CZ gates, and thus it will be small when the vector x is low weighted. Such induced graph will lead to a more non-uniform distribution and lead to bounded range entropy. Knowing that bounded average degree hypergraph states cannot reach n minus small o n magic, we may ask whether random hypergraph states could reach this magic. Before discussing it, we first define two C-uniform random hypergraph state examples. One is that each C hyper H appears with probability 1/2, and the other, the probability is P. Now, notice that since the capital M has a log in it, which troubles us with computing expectation. We convert it to calculate the expected lowercase m. We solve the expected magic problem by reducing it to a counting problem. Here is our theorem for the first example. The expected magic is determined by the number of possible solutions to a related counting problem. The counting problem is quite complicated. Thus, we first take C equals to 3 as a simple example to demonstrate it. It is a binary matrix T and a binary vector X. The first constraint tells us that each column of vector of T should have 0, 1, 0. In other words, they have even ones, as the figure B shows. The second constraint says that for any 3 columns also shows in figure B, x1 multiplying the 1 norm of T2 hallmark product T3, adding x2 multiplying the 1 norm of T1 hallmark product T3, adding the final one should always get 0. For C larger than 3, we should go through all the possible cases as long as the label of X has not intersection with the label of vector T. Due to the time limit, we skip the proof of it. We use the the true alpha replica and some properties of the structure of the hypergraphs here. By solving the counting problem, we can derive the proposition of the upper bound of the lowercase m, which is also a lower bound of capital M. We provide a general bound for any c and alpha and make a more precise analysis when c equals to 3 and alpha equals to 2. In addition, we also follow the same idea to derive the variance of magic when c equals to 3 and alpha equals to 2. By chain of bound, we can find that almost all the hypergraph states have nearly maximal magic and minus small o n. Then we try to generalize our method to a numerical probability P case. Since the problem is much more complicated here, we only consider also c equals to 3 and alpha equals to 2 cases. Even so, it is still no closed form as the theorem shows. So here we numerically draw a figure to show the relation between expected magic and the probability P. To be more intuitive, we let the x-axis to be qubit number n and the y-axis be the expected number of edges. In other words, it is P times n choose 3, nearly P times n qubit. And the different colors of gamma represent different magic scales. For instance, gamma equals to 0.9 as the orange line shows, imply that the magic equals to 0.9 multiplying n. And mu is the slope of the lines. This figure shows that a linear number of hyper edges nearly implies a linear magic scaling. Recalling that a constant average degree implies linear bounded magic scaling. Since the linear number of hyper edges is nearly equivalent to a constant average degree, this numerical result shows that the theorem is tight in the sense of scaling. Until now, you may ask that on the opposite, would all the hypergraph states with large average degrees has n minus small n magic? We answer the question with the study of symmetric hypergraph states, and the answer is no. Here we discuss the magic of two types of specific symmetric hypergraph states. The first is three complete hypergraph states, which connect all triples of vertices with a 3 hyper edge. So the average degree is n minus 1. But after carefully calculation of the SRE of it, by the induced hypergraph method, we find that the SRE M2 goes to 3, but not m minus small o n, as n goes to infinity. Another interesting thing is that m1/2 goes to n in this case, have a large gap with that of M2. Another example is incomplete hypergraph states, which only have one large n hyper edge, but it still has n minus 1 average degree. Then the calculation shows that M2 has a maximal value of log 32 over 11 when n equals to 3 and decrease exponentially to 0 with n. And its m1/2 also increase, but still cannot exceed 2 log 2, 3. We show the figure of induced hypergraphs to replace the tedious calculation. For three complete cases, the induced hypergraphs depends on the number of xi equals to 1. When the number is odd, the induced hypergraphs consist of two complete graphs. When it is even, it is just a complete bipartite graph. For incomplete case, the induced hypergraph has hyperedges acting on all the vertices in one part and a subset of vertices in the other part, as the figure shows. Now we'll make a conclusion with some informal statements. We first propose a systematic approach to calculate the PL polynomial components and SRE with induced hypergraphs. Then with this approach, we find that a bounded average degree implies a bounded magic. After that, by studying random hypergraph states, we find that almost all the hypergraph states have n minus o, small o n magic. And we also numerically show that capital O n three hyperedges should reach capital O m magic with high probability. Finally, we show a difference between M2 and M1/2 in symmetric hypergraph states. And we find that not all the hypergraph states with unbounded average degree should have n minus small o magic. For outlooks, we might generalize our method to study other phase diagonal states and other symmetric states. Another interesting thing is that the difference between M2 and M1/2 on symmetric hypergraph states. We guess that it might be some connection with the distillation and dilution of the states so that we can link them with the resource theory of magic. In addition, with a clear mathematical structure and powerful quantum resources, we think that hypergraph states could be used to study the correlation between different quantum resources, especially for magic and entanglement. Here are the reference. Thank you very much.
Any questions? I have a question. Can you say something about the case alpha equal 1? Because I think I saw somewhere in the slide there is some kind of diversion when alpha goes towards 1. Can you still compute the magic for the case alpha equal 1?
Oh, in general, it is quite difficult for the exponential.
But it's more difficult than say alpha equal 2 or 1/2.
Both of them.
More questions? Yeah, a little more. Can you say something like hypergraph states? They can be used for quantum computation, universal computation. Do you have an example where people relate hypergraph states to a universal computational quantum algorithm, let's say implementing quantum Fourier transform or something like this? Is there like no results? How to use them in practice?
Probably. I don't know such instance. But I know that it can be for polyambiguity. It is a crucial resource state, and for non-ambiguity, the usage of hypergraph states. I have no satisfaction.
Right, then let's thank the speaker again.